So, for the first section of Chapter 5, we want to look at the history of the periodic table. And Chapter 5 is going to be all about the periodic table. And so I think this is going to start to fill in some gaps from some of the things that you have looked at and learned previously. Objectives are going to be in terms of what we know and how we're able to explain it. So we're going to look at the roles of Mendeleev and Moseley in developing the periodic table and be able to describe the modern periodic table, explain how periodic law can be used to predict physical and chemical properties of elements. That concept actually goes hand in hand with the periodic table, knowing it and understanding it. And describe how the elements belonging to a group of the periodic table are interrelated in terms of atomic number. So that's everything we're going to look at in section 1. So let's look at Mendeleev and chemical periodicity. Mendeleev is the name that you should always have associated with the periodic table within chemistry. Often he is kind of recognized as being the father of the periodic table. So Mendeleev is doing work and he's doing research, and he notices that elements were arranged in an order of increasing atomic mass. So notice, okay, he's working with increasing atomic mass. That's where this work kind of starts. With Mendeleev, he noticed that when you arrange elements in order of increasing atomic mass, there ends up being certain similarities in their chemical properties, and these similarities would actually show up at regular intervals. So maybe, the first 10 arranged in terms of periodic mass had some similarities, and then the next 5 had some similarities, and the next 10 after that had some similarities. And he saw these as repeating patterns, and so that's where the term periodic comes from, because the term periodic actually refers to repeating patterns. And so Mendeleev took this information that he discovered and started to actually put it down in table format. And he actually put the elements down in the table with similar properties, and he grouped them together. And this is the beginnings, this is the infancy of the forming of the periodic table of elements. So Mendeleev does this work, and he places all the known elements in his table. He sees that there's several empty spaces left because he placed them based on the elements that they knew at the time, based on their mass numbers and their similar properties. And lo and behold, when you started to organize this information and put it down in a table format, all of a sudden you see that there are spaces. And so the big thing that Mendeleev did, and this is all the way back in 1871, he actually predicted the existence and properties of elements that would fill 3 of the spaces. So he looked at the data he had, he looked at the information he had, and he interpreted out of that information that there's going to be other substances, and these are going to be other elements that fill some of these spaces. And he predicted 3 of them. Not only the elements would be there, but the properties of those elements. And that was in 1871. By 1886, all 3 of those elements had been discovered, and his prediction was shown to be true. So here are the elements that he predicted. We've got the name that he gave for them, and then their actual names and their properties based on their predicted properties and their observed properties. So, very, very interesting. And I guess what I would want to point out is that how accurate his predictions were. Okay, if you look at the predicted properties versus the observed properties, his predictions, based on just the information he had, looking at the other elements around these spaces and what their properties were, his predictions were very, very accurate. Well, this takes us to Moseley and periodic law. So again, what's the history of science, guys? One scientist just does work based on the work that scientists before them have done. So Moseley comes along in 1911. He's an English scientist, and he was able to find, and he was able to show that the elements fit into patterns better when they're arranged according to atomic number rather than atomic weight. So he was able to actually tweak Mendeleev's periodicity, which was based on atomic weight. Now it's important to remember what Moseley discovered is that these characteristics and these properties are driven by atomic number. It worked for Mendeleev because atomic number is part of the atomic mass or the atomic weight. So Mendeleev, without even knowing it, was still grouping these things by their atomic number because atomic number is a part of atomic weight. Okay, and so Moseley says, well, there must be this law, and we call it the periodic law, which states that physical and chemical properties of the elements are periodic functions of their atomic numbers. So now what we know is that it's the atomic numbers that drive these things, that drive these properties that are physical and chemical. And in fact, you guys know, we can actually drill this down even farther, because atomic number is ultimately just the number of protons. And we've already said the number of protons is what identifies what an element is. You can never change the number of protons. If you change the number of protons, you change what the element is. So ultimately, what we now know, what we're saying, is that the number of protons, which gives the identity of an element, is the thing that drives the chemical and physical characteristics of that element. And so there's a table here that shows periodicity of atomic numbers. So here is on the left, group 18, the element and atomic number. So helium is 2, neon is 10, argon is 18, right? And the difference in atomic numbers between them, 8, 8, 18, 18, 32. Notice, if you look at group 1, completely different set of elements, from lithium to sodium to potassium to rubidium, cesium, francium, right? And notice the difference in atomic numbers. Same pattern, 8, 8, 18, 18, 32. This brings us up to the modern periodic table, which is something that you guys have had at least some introduction to. Now you're going to spend this week actually studying it and memorizing large portions of it. The periodic table is an arrangement of the elements in order of their atomic numbers, so that elements with similar properties fall in the same column or group. Right? So columns are groups, and the modern periodic table, the one that you've used and you've looked at occasionally, is arranged according to atomic number. And what that arrangement does, by doing it by atomic number, makes sure that you have elements with similar properties end up in the same group. That is the modern periodic table. This periodic table that we use comes from the work of Mendeleev first, and then Moseley coming up with periodic law based on Mendeleev's work. Alright, so now we're going to look at section 2, and we're going to, in this section, look at electron configuration, which you've already been introduced to. We're going to look at electron configuration and how that relates to the periodic table and what we've already talked about. So we're going to need to be able to explain the relationship between electrons and sublevels and the length of each period of the periodic table, and locate and name the 4 blocks of the periodic table and explain the reasons for these names. So we're going to jump right into that now. Discuss the relationship between group configurations and group numbers. Describe locations in the periodic table and the general properties of the alkali metals, the alkaline earth metals, the halogens, and the noble gases. Guys, I'm going to say at the outset here, this is a week where you need to be willing to do a lot of memorization. Okay? Just to lay that out, you need to be willing to do a lot of memorization. And most of that memorization is going to be focused on the periodic table. So please, be thinking about committing yourself to that work this week. All right, so let's look at periods and blocks of the periodic table. So we know that the periodic table that we use is arranged in terms of atomic number, and by doing that we get groups or families, and the elements in a group have similar properties. Okay, so let's break this down a little bit more. Elements are arranged vertically in the periodic table in groups that share chemical properties. We know that. But elements are also organized horizontally in rows. The rows are called periods. So the columns are called groups. Okay? And the rows are called periods. the length of each period, so how far that period is from left to right, is determined by the number of electrons that can occupy the sublevels being filled in that period. So now we've got to take what we learned last chapter in terms of filling sublevels, and we apply this to understanding the periods within the periodic table. So the periodic table is divided into 4 blocks. We have the S block, the P block, the D block, and the F block, and those should sound familiar. The name of each block is determined by the electron sublevel being filled in that block. So where are the electrons filling? If the electrons are filling an S sublevel, that element is going to be in the S block of the periodic table. If the electrons are filling a P sublevel, they're going to be in the P block, a D sublevel, an F sublevel, so on and so forth. Don't worry about this. Alright, so here's a picture of the periodic table. Okay, and you can see here that there's lots of different things on here. And you've got to be able to read it. So you've got your color coding, you've got your semiconductors, you've got the metals, and the metals are broken down in alkali, alkaline earth, transition, and others, and then the nonmetals are broken down into halogens, noble gases, and others, and that's all color coded, as well as we have in each the atomic symbol, the atomic number, the atomic mass, and the halogen electron orbital notation. So if we look at group 1, that's going to be the group all the way over. Okay, group 1 to the left. Group 1 are the alkali metals. What falls under the alkali metals? Lithium, sodium, potassium, rubidium, cesium, and francium. And in their pure state, all the alkali metals have a silvery appearance and are soft enough to cut with a knife. Okay, so sodium, we describe sodium as a metal, but it's a soft metal. Okay, you could take a butter knife and cut sodium in half. If we move over to group 2, those are called the alkaline earth metals. And these are beryllium, magnesium, calcium, strontium, barium, and radium. Now notice, guys, again, we're talking about groups, so these are the columns. And when you look at a periodic table, these columns are going to be numbered. And group 2 metals are less reactive than alkali metals. You see, alkali metals are very, very reactive. Sodium is unbelievably reactive. Sodium in water gives you an explosion. That's how reactive it is. But they're still too reactive, the alkaline earth metals, that is, are too reactive to be found in nature in a pure form. So even though they're a lot less reactive than the alkali metals of group 1, they're still pretty reactive. Now hydrogen's interesting. Okay, hydrogen has an electron configuration of 1s1. You know that. But despite the s1 configuration, it does not share the same properties of the elements of group 1. So it's not an alkali metal. And so hydrogen ends up being unique. Okay, and being unique, it has kind of its own place, so to speak, in the periodic table. Like the group 2 elements, helium has an S2 group configuration, but it's part of group 18. Why is it part of group 18? This should make sense. Okay, I want to work through this. Its highest occupied energy level is filled, right? Because its highest occupied energy level is an S sublevel, and S can only have up to 2 electrons in it. Helium has 2, so that S is filled, which means there's no empty spaces, which means helium is not very reactive with anything. And so we put it with group 18, we put it with the noble gases, because the noble gases are not very reactive, because the noble gases have 8 electrons in their outer shell. Okay, so you got to understand, whether or not something is reactive, guys, that is a statement of whether or not it easily undergoes chemical changes, okay, or will undergo chemical reactions. Whether or not something is reactive is a function of how many electrons or how many spaces for electrons it has to share electrons. Something that has a completely filled outer shell, like helium, which the S sublevel has the 2 electrons, doesn't have a lot of spaces, doesn't have a lot of opportunity to do things with other elements, and therefore it doesn't react a lot. The noble gases are called noble gases because they have a filled outer shell of 8 electrons. They're not going to be reactive. Why is it that you can take helium and suck it into your lungs, right, out of a balloon to make your voice sound funny and not worry about any bad side effects or anything? Well, because helium's not very reactive. Okay, so you've got to start to understand that this concept of reactivity has to do with the electrons. So what's the relationship between periodicity and electron configurations? We can see this here. Period number is, if the period number is 1, the number of elements in the period is 2. The sublevels are the 1s, right? That's hydrogen on one end, helium on the other. If the period number is 2, the number of elements in the period is 8. Sublevels in order of filling are 2s and 2p. If the period number is 3, you've got 8, and you can just see how this chart goes. So how would we work these out in terms of a problem? Without looking at the periodic table, identify the group, period, and block in which the element that has the electron configuration, that's xenon 6s2, is located. So how do we do that? First, without looking at the periodic table, write the electron configuration for group 1 element in the 3rd period. Is this element likely to be more reactive or less reactive than the element described in A? That's the first thing we're going to do. Moving on. The element is in group 2, as indicated by the configuration of NS2. So we've got that. It is in the 6th period, as indicated by the highest principal quantum number in its configuration, which was 6. So the element is in the S block, because S is the sublevel that's filled. In a 3rd period element, the highest occupied energy level is the 3rd made energy level. So that's the 3 number. 1s, 2s, and 2p levels are completely filled. So the element has the following configuration: 1s2, 2s2, 2p6, 3s1, or Ne3s1. Because it is in group 1, the element is likely to be more reactive than the element described in A, which is in group 2. Now what I would suggest, guys, is you kind of backpedal and kind of look over this problem several times to see how it was worked out. You're also going to want to make sure you read in the book this section, which will fill this out a little bit more. Basically what we're doing here is taking what we learned last chapter and how to do these electron configurations and what we know about the periodic table and how it's organized, and put the two together. So the D sublevel first appears when n equals 3, right? We learned this. The 3D sublevel is slightly higher in energy than the 4s sublevel, so these are filled in the order of 4s 3D. We learned that. The D block elements are metals with typical metallic properties that are often referred to as transition metals. So there's your D block, SP and D. There's your D block metals. So let's look at another problem. An element has the electron configuration of 4d5, 5s1. Without looking at the periodic table, identify the period, block, and group in which the element is located. Then consult the periodic table to identify this element and the others in its group. So what does this look like? The number of the highest occupied energy level is 5. We know that based on the electric configuration. So we know that the element is in the 5th period. There are 5 electrons in the D sublevel, which means that it is incompletely filled. You know that because you know how many electrons can go in a D sublevel. The D sublevel can hold 10. There's 5 orbitals in the D sublevel. 2 electrons per orbital means 10. In this case that we're given, it only has 5. Therefore, the element is in the D block. The D block elements. For D block elements, the number of electrons in the NS sublevel 1 plus the number of electrons in the N-1 D sublevel 5 equals the group number 6. So we've just identified everything the question asks us to identify. So this is a group 6 element, molybdenum. The others in the group 6 are chromium, tungsten, and seaborgium. Again, I would back these up. I'd listen to this a couple of times. I'd have your book opened, read this section, start to fill in whatever blanks there may be. And then we go on to the P block. Remember, we said there's S, P, D, and F. Okay, the P block elements consist of all the elements in group 13 through 18 except helium. We already talked about helium. It's the S block. It's unique in at least that sense. P block elements together with the S block are called the main group elements, and you can tell visually the main group elements just by how the periodic table is laid out. And the properties of elements of the P block vary greatly, so there is no standard here. Okay, at its right hand end, the P block includes all the nonmetals except hydrogen and helium. So you've got nonmetals. All 6 of the metalloids are also in the P block. Metalloids are the same thing as that line that between where metals transition to nonmetals. At the left-hand side, the bottom of the block, there are 8 P block metals. So this hopefully gives you an idea. I mean, there's lots of variation in properties within the P block. Then we get to group 17. These are the halogens. I've mentioned these already. Fluorine, chlorine, bromine, iodine, astatine. Halogens are the most reactive nonmetals. Okay, so that's important. Most reactive, they're all nonmetals, very, very reactive. They react vigorously with most metals to form examples of the type of compound known as salts. So these are where we can get a lot of our metallic salts. You know about chlorine because of sodium chloride, but there's other metallic salts, potassium chloride, okay, calcium chloride, but they don't only have to be with chlorine as well. Metalloids or semiconducting elements are located between nonmetals and metals in the P block. The metals of the P block are generally harder and denser than S block alkaline earth metals, but softer and less dense than the D block metals. If I were you guys, I would listen to this section once, and then I would go back and with a periodic table open, listen to this section again. I think that would be beneficial. So another sample problem here. Without looking at the periodic table, write the outer electron configuration for group 14 element in the second period. Then name the element and identify it as a metal, nonmetal, or metalloid. Pretty intense. How are we going to do this? The group number is higher than 12, so we know that the element is in the P block. Total number of electrons in the highest occupied S and P sublevels is therefore equal to the group number minus 10. So 14 minus 10 equals 4. 2 electrons are in the S sublevel, so 2 electrons must also be present in the 2p sublevel. That should make sense. So the outer electron configuration is 2s2, 2p2. Hopefully that follows for you guys. The element is carbon, which is a nonmetal. In the periodic table, the F block elements are wedged between groups 3 and 4 in the 6th and 7th periods. Position reflects the fact that they involve filling of the 4F sublevel. First row of the F block are the lanthanides. They are shiny metals similar in reactivity to the alkaline metals. And then the second are the actinides, are between actinium and rutherfordium. And they are the radioactive elements. So how do we look at this? Name the block and group in which each of the following elements is located in the periodic table. Then use the periodic table to name each element. Identify each element as a metal, nonmetal, or metalloid. Finally, describe whether each element has high reactivity or low reactivity. So here we are. We've got these 2 examples and a couple more. We're going to look at all these. The 4F sublevel is filled with 14 electrons. The 5D sublevel is partially filled with 9 electrons. Therefore, this element is in the D block. The element is the transition metal platinum, which is in group 10 and has a low reactivity. Incompletely filled for B, the incompletely filled P sublevel shows that this element is in the P block. Total of 7 electrons are in the NS and MP sublevel, so this element is in group 17. So it's a halogen, it's chlorine, and it's highly reactive. For C, the element has a noble gas configuration, is in group 18 in the P block. It's argon, which is unreactive nonmetal, a noble gas. And then for D, you've got the incomplete 4F sublevel, which shows that the element is in the F block. It's a lanthanide, and group numbers are not assigned to the F block. The element is samarium. All the lanthanides are reactive metals. Alright guys, we're going to look at section 3. This has to do with electron configuration and periodic properties, and this will finish up the chapter for us at this point. Our objectives are to define atomic and ionic radii, ionization energy, electron affinity, and electronegativity. Compare periodic trends of atomic radii, ionization energy, and electron negativity, and state the reasons. Define valence of electrons and state how many are present in atoms of each main group element. Compare the atomic radii, ionization energies, and electronegativity of the D block elements with those of the main group elements. Alright, so what is atomic radii? So you know what the word radius is, so hopefully that will help move you along in understanding this. The boundaries of an atom are fuzzy, meaning we now know that there cannot be a set boundary line. Atoms' radius can vary under different conditions. And so we can compare different atomic radii, but in order to compare atomic radii, that is the radius of any given atom, we need to actually make the measurements under specified conditions because these can vary. So the atomic radius may be defined as 1/2 the distance between the nuclei of identical atoms that are bonded together. So that's your textbook definition. So atoms tend to be smaller the farther to the right they are found across a period. So that's a trend about the periodic table that you need to be familiar with. The closer to the left, the larger the atoms. The closer to the right, the smaller the atoms. At least that's a tendency. The trend to smaller atoms across a period is caused by increasing positive charge of the nucleus, which attracts electrons toward it. So, what does that mean? Well, the farther you move to the right, guys, on the periodic table, the more protons there are. The more protons there are, the more positive charge there is, the stronger the attraction of the positive charge for the negative, which pulls the electrons toward it, tending to make the atom actually smaller. Atoms tend to be larger the farther down in a group they are found. So the top of the group, the atoms are going to be smaller than they are at the bottom of a group. The trend to larger atoms down a group is caused by increasing size of the electron cloud around an atom as the number of electron sublevels increases. So hopefully that makes sense. So here are the periodic trends of radii. You look at these charts. As you go down, it increases. As you go from left to right, it increases. Okay. So, how does this play out in a problem? Of the elements magnesium, chlorine, sodium, and phosphorus, which has the largest atomic radius? Explain your answer in terms of trends of the periodic table. So, sodium has the largest atomic radius. Why is that? All the elements are in the third period. Of the four, sodium has the lowest atomic number and is the first element in the period. Atomic radii decreases across the period. Let's talk about ionization energy. An ion is an atom or group of bonded atoms that have a positive or negative charge. So in order to understand this, you got to understand at the outset what an ion is. Any atom with a charge, whether it be a positive charge or a negative charge, is called an ion. So an example would be sodium. Sodium generally easily loses an electron. If it loses an electron, it loses a negative charge, which means it has more positive charge than negative charge, and it forms a positive ion, which we represent as Na+. Any process that results in the formation of an ion is referred to ionization. So anything, regardless of what happens, if it results in the formation of an ion, it is ionization. The energy required to remove one electron from a neutral atom of an element is the ionization energy, IE. So in general, ionization energies of the main group elements increases across the period. So the increase is caused by increasing nuclear charge. Well, we know that the nuclear charge increases because as you go from left to right across the period, the number of positive protons increases, which means the strength of the attraction increases, which means you're going to have more energy to pull that electron away from that higher positive charge, which means your ionization energy is going to increase. A higher charge more strongly attracts electrons in the same energy level. If we're looking at main group elements, ionization energies decrease down the group. So electrons removed from atoms of each succeeding element in a group are in higher energy levels, which means they're farther from the nucleus, which means it doesn't take as much energy to pull them away from the positive charge of the nucleus, and the electrons then are removed more easily. And we can represent ionization energy in this graph formation as you look at atomic numbers increasing left to right on the x-axis. If you look at first ionization energy increasing from the bottom to the top on the y-axis, notice from the ionization energy difference from hydrogen to helium, from lithium to neon, to that's as you move from period 2 to 3, as you move from period 3 to 4, you see those trends there. So consider two main group elements, A and B. Element A has a first ionization energy of 419 kilojoules per mole. Element B has a first ionization energy of 1,000 kilojoules per mole. The side of each element is more likely to be in the S block or P block. Which element is more likely to form a positive ion? How do we work through this? Element A has a very low ionization energy. It means that the atoms of A lose electrons easily. Element A is most likely to be an S block metal because ionization energies increase across the periods. Element B has a very high ionization energy, which means that the atoms of B have difficulty losing electrons. Element B will most likely lie at the end of a period in the P block. Element A is more likely to form a positive ion because it has a much lower ionization energy than element B does. Alright, let's talk about electron affinity now. The energy change that occurs when an electron is acquired by a neutral atom is called the atom's electron affinity. Electron affinity generally increases across periods. So this again, as you go left to right. Increasing nuclear charge along the same sublevel attracts electrons more strongly. So what's going on here? As you move left to right, you increase number of positive particles, you increase positive charge, you increase the atom's attractiveness to negative electrons. Electron affinity generally decreases down groups. The larger an atom's electron cloud is, the farther away its outer electrons are from its nucleus, the less attractive that positive charge is. Now, with ionic radii, a positive ion is known as a cation. Easy way to remember that is the T looks like a plus sign. The formation of a cation by the loss of one or more electrons always leads to a decrease in atomic radius. So, think about this. If you lose electrons, you lose negative charge. You have more positive charge than you have negative charge. The positive charge is going to pull the negative charge that's left in closer, and the atomic radius decreases because of that. The electron cloud actually becomes smaller. The remaining electrons are drawn closer to the nucleus by its unbalanced positive charge. This is ionic radii. A negative ion is known as an anion. Just remember, putting A in front of everything means take away. So now you're taking away. It's negative. The formation of an anion is by the addition of one or more electrons, which always leads to an increase in atomic radius. Right? So this is the exact opposite of the cation. I've added electrons, I've added negative charge. There's more of a pulling away from the positive charge in the nucleus. The radii of the anion is bigger. Cations anionic radii decrease across a period. So the electron cloud shrinks due to increasing nuclear charge acting on the same main energy level. This is the same as we talked about before with atomic radii, guys. You move across the period, you're increasing positive charge. It pulls everything in closer together and tighter. The outer electrons of both cations and anions are in higher energy levels as one reads down a group. There is a gradual increase of ionic radii down a group. Let's talk about valence electrons. Chemical compounds form because electrons are lost, gained, or shared between atoms. So I've mentioned this, guys. Chemical reactions form due to electrons on the outside of an atom. The electrons that interact in this manner are those in the highest energy level. And the highest energy level ends up being the outside electrons of any particular element. So the electrons available to be lost, gained, or shared in the formation of chemical compounds are referred to as valence electrons. They're often located in incompletely filled main energy levels. They're the ones on the outside. Think of them as the outside shell. The electron lost from the 3s sublevel of sodium to form the sodium ion is a valence electron. That's an example of what we're talking about. Electronegativity has to do with valence electrons holding atoms together in chemical compounds. In many compounds, the negative charge of the valence electrons is concentrated closer to one atom than the other. And this gives electronegativity, which is a measure of the ability of an atom in a chemical compound to attract electrons from another atom in the compound. Electronegativities tend to increase across periods or decrease or remain about the same down a group. So, well, there's a problem like this. You've got the element gallium, bromine, calcium. Which has the highest electronegativity? Explain your answer in terms of periodic trends. They're all in the fourth period. Bromine has the highest atomic number and is farthest to the right in the period. So bromine should have the highest electronegativity because electronegativity increases across periods.